Here we have a cyclohexane that has two substituents. It has a chlorine in the up position and a methyl in the down position. And we want to put these on our chair diagrams. So the first one's pretty simple. We just want to make sure that the chlorine is put on an up position. And I'm going to pick right here to put it. The chlorine is up and axial. The methyl needs to be down, and it needs to be on the carbon that's right beside the chlorine carbon. So it'll have to be on this carbon, and it needs to be down, so the methyl group will go right here. And it's also axial. When we do the ring flip, we'll want the chlorine to be up but equatorial. So we'll need to pick a position where the chlorine can be up and equatorial. This is one. The equatorial here is in the up position. We can put the chlorine right there. We need to put the methyl group on the net carbon that's right next to it, and it needs to be in the down position, and it needs to be equatorial, and so we'll put it right here. So these are both equatorial. And they haven't changed position. The methyl group is down in both pictures. The chlorine is up in both pictures. Okay, so let's do some more practice. You are going to have to make sure that you can draw all 12 positions accurately. There we go. So here we have a methyl in the up position. The methyl is up, and the ethyl is down. And they're right next to each other, 1, 2. So we'll put our methyl group here. It could be in any of the up positions. Any of the up positions would have been correct. We need to put the ethyl on a neighboring carbon, and it needs to be down. So it'll have to be equatorial. Axial. Okay, because this one has to be up and that one has to be down, and they have to be right next to each other. When we do the ring flip, we'll want the methyl group to be up and equatorial. We'll put it right here. Next carbon over, we want the ethyl to be equatorial and also down. So that's where that'll go. Well, let's do a different example. So in this example, we have a methyl that's up, and our ethyl is also up. I'm going to move this up just a little bit. Move that guy out of the way. Okay. So we could pick any place to put our methyl. It could be here, here, here. It could also be here, any of these that's up, but just to pick one, I'm going to pick that one. Now the second carbon needs to have an ethyl, and the ethyl needs to be up, so it'll have to be here, and that makes it equatorial. So our methyl is axial, and our ethyl is equatorial. When we do our ring flip, we'll want our methyl to be up and equatorial, so we'll put it right here. That's one of our positions that's equatorial and in the up position. Then we'll go to the next carbon, and we need this one to be the ethyl to be up and it's equatorial on this diagram, so we need it to be axial. So we'll put it right here. Right. Our last example, move these up. I've got a methyl that's up, and then a bromine that's up. So we'll put the methyl here. I'm nothing but predictable. Then we need to skip one. This is 1, 2, 3. 1, 2, 3. We need the bromine to also be up. So the up position on the third carbon is axial, so we'll put it right here. Both of these are axial. We need in the ring flip for them to be up and equatorial. So this is an up equatorial position. We need to skip the second carbon and go to the third carbon. We need it also to be up and equatorial. So our bromine will go right there. Comparing the stability of the chair conformations. Okay, so chairs are more stable when large groups are in the equatorial position. So if they're along the equator, then they can spread out and they don't interfere with each other. So if one group is equatorial and the other is axial, you can refer to a table like this one to see which is more important. Now, a large T-butyl group will almost lock the position into the equatorial position because it's so much more stable that way. And you can see a chlorine has a little effect, hydroxy a little more, a methyl group a bit more, and as the groups get larger, they get more favorable to put them in that equatorial position. So let's look at a couple of disubstituted cyclohexanes and see which is the lowest energy conformation of each. Okay. So here's our first one. We've got a methyl that's up, and we have a methyl that's down. Okay, so I'm going to put my first methyl. We'll do pink and purple. We'll do our pink methyl, and we'll put it in the up position. The other methyl needs to be in the down position on the next atom, and so it would be right here. So here we have both of them in an axial position. When the ring flips, the pink methyl will be up, but it'll be equatorial. We'll put it right here. On the next carbon over, we'll need to have a methyl that's down and equatorial. That will be right here. So this would be the more stable because both methyl groups are in the equatorial position. Okay, so here we've got the next one. We've got a methyl that's up and isopropyl that's up. So we'll put our methyl. We'll make it a blue methyl this time. Okay, so this group then needs to be on the next carbon, and it needs to be up. So it will be here. We'll just give it a Y. Okay, so the methyl is axial, so it needs to be equatorial on the next drawing. So we'll put it here. And this isopropyl group needs to be on the next carbon. It needs to be up. So it'll have to be right there. Because this is a large bulky group and it's equatorial here, this will be the more stable form. Okay, so now I'm going to have to get out 3 colors. So we've got a methyl that's down. We've got a chlorine that's down. And we've got a chlorine that's up, and we'll do it in purple. Okay, so let's start with our methyl that's down. I'm going to put it, this is my favorite place to start, I guess, so we're going to make it down. It'll have to be equatorial. So there's our methyl. On the next carbon, we have a chlorine that's down, and that puts it in an axial position. The next carbon, right after that one, has a chlorine that's up, and that puts it in the axial position. On the next, on the flipped ring, the methyl group needs to be axial and down. So we can put it right here. Axial and down. We need to put our 2 chlorines here. I didn't do the purple one. Okay, so this one is axial and down, so it needs to be equatorial and down. The next one needs to be equatorial and up. So if we compare these, we look at our diagram above. Chlorine has an interaction of an effect of 2, but the methyl group has a greater effect, and so this is our more stable because it has the methyl group out to the side. We use the table to tell us that. Okay, so here we've got a methyl that's down, a methyl that's up, and I will try and use the 3 colors this time, and a T-butyl that's up. And sorry, get this so you can see it. All right, so we'll start with the blue methyl. It's down, so we'll put it in a down position. On the next carbon, we've got a methyl that's up, and so we need to do it in pink. It needs to be a pink methyl. And on the next carbon, we've got a T-butyl that's up. And the T-butyl kind of looks like a tree. It's very big. So that's one configuration. The other configuration, we have a methyl that's down, our blue methyl. We'll put it here. We have a methyl that's up on the next one. We'll put it here. And we've got a T-butyl that's also up, and it would go here. Now on this one, this first one, we've got 2 methyls in equatorial position and a T-butyl in an axial position. Here we've got the 2 methyls are in axial, and the T-butyl is equatorial. If we look at our chart at the top of the page, we'll discover that the T-butyl has much more effect, and so we expect that this one will be the more stable. Cis-trans isomers. Okay, if they're cis, they're on the same side of the ring, so both these methyl groups are up. So they would be cis, And since they're next to each other, we would get these rings, axial, equatorial, axial, equatorial. If they're trans, they're across the ring. That's what trans means. And that means that they're across the ring and one is up and one is down. We'd expect them both to be axial or both to be equatorial. You can remember this because trans means across. That's just what it means. And cis looks like a C. These are different compounds with different properties, and to interconvert them requires breaking of bonds. Now, it's just an important aside to realize that there are many polycyclic systems. We have steroids, testosterone and estradiol, that have 6-membered rings and one 5-member ring stuck together. So many naturally occurring rings. Diamonds are based on a 6-member ring that's locked in a chair conformation. Note how stable that is. And every carbon is bonded to 4 others. So diamonds are just one big, large molecule. That's why they're so hard.